Very good morning, my dear students. Today I would like to present a topic of paper DEMATH1 course Complex Analysis 1, and title of my topic is Zeros of Analytic Functions. The main goal of this topic is to define one of the important properties of analytic function, namely zeros of analytic functions and some related results. So first we start with a definition. A function from f d to c, d must be a domain, is said to be differentiable at some point, say z0 belongs to d, if the limit this f of z minus f of z0 by z minus z0, and this is equivalently this, if these two limits exist. Okay, so when this is the case, the value of the limit is denoted by the notation f dash z0, and we call it the derivative of f at z0. So there are so many functions which are differentiable. For example, if we consider the constant function, polynomial function, and also the exponential function, all are differentiable in the entire C. Now we consider one example. F of z is equals to modulus of z squared, and it is very easy to show that this function f is differentiable at the point 0, because the limit this is equals to 0. So the limit exists and equals to 0. So this function is differentiable at the point z equals to 0. But this function is not differentiable in any other point of the neighborhood of 0. Okay. So because this function is not satisfy our well-known result, Cauchy-Riemann equation, at the other point other than 0, so there exists a complex function. So there exists a complex function which is differentiable at a given point but not any neighborhood of that point. And this definition, okay, sorry, this example leads to the following definition. A function if is said to be analytic or holomorphic, okay, at a point say A belongs to the domain D. If we taking the function f is defined on a domain D, if it is differentiable at every point, okay, every point of some neighborhood of A. Okay, so the analyticity of a function is the global properties. So if a function f is analytic in the neighborhood of that point, then we say this is analytic. Okay, but the previous example shows that this function is differentiable but not analytic. There are so many examples of analytic function. The exponential function e to the power z, sin z, all polynomial function, are all are analytic function. We now discuss the zeros of analytic function using the Taylor series expansion as a tool. Okay, so for this we suppose that f is analytic function. So suppose f is analytic function and f is not identically zero in an open set D where f is defined. Okay, so then then the function f, then this f admit a Taylor series expansion about the point A, right? As we know, the Taylor series expansion of A about the point A is written as this: fz equals to this plus and so on. And by the assumption of the function that f is not identically zero in the domain. Okay, so f is not identically zero, and this implies that all the coefficient of this Taylor series expansion is not zero, it's not vanishes. Okay, so we can say that not all the coefficient ak vanishes, that means there exists a positive integer say m, which is greater than or equal to 1, such that all the coefficient of the Taylor series expansion up to m minus 1 is 0, but the am is not equals to 0. So we say, so now we can say that f has a 0, this is finitely many, finite 0, order 0, zeros of order m, and we write it as that fz is equals to z minus a to the power m gz, where g is an analytic function, and of course this g of a is not equals to 0. So if we summarize all the all these things, we have the following definition. If f is a function from G to C, where G is a domain that is open connected, and this function f is analytic, and suppose that A belongs to G as an element which satisfy that f of A is equals to 0, then A is a 0 of f. Okay. F is a 0 of f of order, or we can say multiplicity, which is greater than equals to 1, say order m greater than equals to 1, if there exists analytic function g from G to C such that f of z can be written as in the following expression, where okay, so these are the zeros of analytic function. Now we give another definition. A zero of an analytic function say f is said to be isolated 0. Okay, isolated if it has no other 0, that is f has no other zeros in the neighborhood of that zeros. Okay, in the neighborhood of that zeros. So this is the only one zeros of this analytic function. In this case, we say that the zeros of the analytic function is isolated. Okay, and one very important result related to this, that every zeros of an analytic function is isolated. Okay, so write down the theorem that every zeros of an analytic function f, which is not identically zero, is isolated. Now we state one very important theorem, or we can say result of complex analysis, which is very important. So this theorem states that let G be a connected open set, that is, let G be a domain, and f is a function from G to C, then the following are equivalent. Following are equivalent. Number one, f is identical equals to 0, and number B, there is a point A in G such that the nth derivative at that point is 0 for every n is greater than 0. And number C, the collection of all zeros of f has a limit point in G. So this is the statement of the theorem. Now we consider two examples to show that this G is open connected must be needed, otherwise the theorem is failed. So for this, we considering one example. Suppose considering one example, this if from to C, by defining the function f of z is equals to 1 for modulus of z less than 1 and 0 for modulus of z greater than 3. Then clearly f is holomorphic function in the domain and here set of all zeros is coming from mod z greater than equals to 3, but if is not identically equals to 0, because this domain is not open connected, it's not connected set. So in this theorem, the connectedness of domain must be required. And now we're considering another example. We're considering one real variable, real valued function defined by fx equals to e to the power minus 1 by x if x is greater than 0, and this is equals to 0 when x is less than 0. And here, for x not equals to 0, f has derivative of all order, and it is easy to check that derivative of f for x less than equals to 0 is 0. However, this function a does not vanishes in R. But in case of, so we can say that the uniqueness theorem shows that this is not the case for the function of complex variable. Okay, so if we considering real variable, then we getting one function which has infinitely zeros, infinitely, that is the nth derivative of that point is 0, but this is not identically 0. But by this theorem, if f is identically 0, then this hold. And conversely, if there is a sum a for which the nth derivative is 0 for all n, then f is identically 0. But this is not hold for the case of real variable. Now let's another example. And in this example, we shows that the domain, the limit points of zeros, is lies in a domain is not superfluous. Okay, so for this we considering say fz equals to sine 1 by 1 minus z, then f is analyzed in the unit digits, and set of all zeros of this function is given by 1 by minus n pi for all n belongs to n. And we can easily see that this tends to 1 as n tends to infinity. So set of all zeros has a limit point 1, and which and this limit point is not a element of the domain D. Here D is the unit digits, and so set of all limit zeros has a limit point, but f is not identically equals to 0 by the previous theorem. Okay, because this limit point is not belongs to the domain, and also f is not analytic. If is not analytic at 1. Okay, this is the reason that set of all zeros has a limit point, but f is not identically equals to 0. Okay, and there are some other consequences of the this set of all zeros. Using this uniqueness theorem, we can say this first part as a uniqueness theorem. Okay, using this theorem, we prove some result which is hold on the complex analysis, real analysis. For example, this identity sin square z plus cos square z1. There are so many identities we can prove using this the above theorem. So okay, thank you all.